In this section, we're going to be using derivative to solve real-life problems. Typically in these questions, we're going to be faced with several rates of change. Some of those we'll know, but one is going to be unknown. And our task will be somehow to figure out a relation, a formula that expresses the unknown rate of change in terms of the other ones that are known so that we can go ahead and find the unknown rate of change. I know that this sounds confusing right now, but as I begin with example 1, I'm hoping that you'll see exactly how we're going to put that into practice. In example 1, we are being told that we have a spherical balloon, so a balloon that is in the shape of a sphere. And this balloon is leaking air so that its surface area is decreasing. The surface area is decreasing at the rate of 1 inch squared per second. At the moment when the radius is 6 inches, how fast is the volume decreasing? So if you notice here, the radius and the volume are changing with respect to time. We know that dA by dt, the rate of change of the area with respect to time, here area, I really mean surface area, this is equal to -1 inches squared per second. And I put the -1 because we are losing air. The air is leaking out of this balloon. So that will be represented with that negative. And what we need to do is to find the volume, dV by dt, exactly when the radius is equal to 6 inches. So I have area and I have volume going on. Now the volume of a sphere is equal to 4/3 pi r cube. And I know that the surface area of a sphere is equal to 4 pi r squared. So if you notice right here, if I go back to volume, and if I try to find the rate of change of volume with respect to time, so dV by dt, I am going to get that dV by dt is going to be somehow in terms of dr by dt. And I know that because remember, time is radius is changing with time. So I will be differentiating implicitly. dV by dt is going to be equal to 4/3 pi times 3 times r squared. But again, because radius is changing with time, we're going to multiply that by dr by dt. The 3's are going to cancel out, and I'm going to have that dV by dt is equal to 4 pi r squared times dr by dt. So now you notice that I have obtained a formula, a relation that is relating dV by dt, is expressing dV by dt in terms of another rate of change, dr by dt. The only thing though is that I don't know dr by dt. This particular quantity right here is unknown. So then that means that perhaps I can find dr by dt by using surface area. Because if you remember, I do know the rate of change of the surface area. If I differentiate, again, if I differentiate implicitly, dA by dt is going to be equal to 8 pi r times dr by dt. dA by dt is -1 equals 8 pi r times dr by dt. And now I should be able to solve for dr by dt because exactly when r is equal to 6 inches, I know that I can find this rate of change. Remember that everything has to happen at the end when r is equal to 6 inches. Now, my advice is for you not to rush to substitute r before differentiating. You always want to differentiate first and then substitute the given radius. This is always the practice with related rate problems. First differentiate and then substitute values for the radius, for example. So I'm going to have -1 equals to 8 pi times 6 times dr by dt. And then when I rearrange everything, I'm going to get that dr by dt will equal to -1 divided by 48 pi. I'm just skipping a few steps in there. So now that I have dr by dt, I can take that value and substitute it right there. That means that we're going to have that dv by dt is going to be equal to 4 pi. Again, because I already differentiated, I can substitute the value for the radius, so 6 squared times -1 over 48 pi. And when I simplify that by canceling pi's, reducing, I should end up very nicely with -3. So that's going to be the value of dv by dt. Now the units, again, I want you to look at the notation. The volume is in the numerator, that means inches cube. And the time is in the denominator, so then that means seconds. And that's going to be the unit for the rate of change of volume with respect to time. When you write your conclusion up, you want to be able to now say, okay, therefore, for example, when the radius is equal to 6 inches, the volume of the balloon decreases. And this is what I want to emphasize here. If you write the word decreases, then you don't have to include the negative. The word replaces the negative sign. So you say the volume of the balloon decreases at a rate of 3 inches cubed per second. Somehow, if you include the negative and you write the word decreases, it's like expressing double negation. Doesn't make sense. So if you write the word decreases, just omit the negative sign. It decreases at a rate of 3 inches cubed per second. In this question here, we have the following. A 5-meter ladder leans against a wall. The bottom of the ladder is 1.5 meters from the wall at time t equals 0. So at the very beginning, right before anything starts, we know that the bottom of the ladder, if we go to this diagram right here, I am imagining that this is the initial position of the ladder right here. T is equal to 0. So this horizontal distance is going to be 1.5 meters. All right, continue reading. And then the ladder slides from the wall at a rate of 0.8 meters per second. So imagine the ladder sliding and sliding. First, the initial position, and then the top is going down and down because the ladder is sliding away from the wall. The question is to find the velocity of the top of the ladder at time t equals to 1. Something very important to figure out here is that the top of the ladder is moving down, the bottom is moving away from the wall. The difference is that the speed in which the bottom is moving away from the wall is constant, whereas the speed of the top of the ladder, in which it is going down because the ladder is sliding downward, the speed of the top is actually varying, is not constant. And if you wonder why, it's all because of the physical aspect of what is happening here. Gravity is a force that it acts down. So then, because the top is going downward, it is under the effect of gravity. So gravity is causing acceleration, is accelerating, right? Is affecting acceleration of the top of the ladder. And as soon as we have acceleration, then we know that velocity is changing, therefore speed is changing. Whereas the bottom is not moving in an up-down direction. It's actually moving horizontally. So gravity is not acting on the bottom of the ladder. So that's the speed of the bottom of the ladder remains constant at every particular time. So given that, what I want to do in this problem is to create a cleaner diagram. So I'm going to transition to the bottom right here, and we're going to let x represent the horizontal distance from the bottom of the ladder to the wall, and h is going to be the vertical distance from the top of the ladder to the ground. So with that in mind, let's see, what are things that we know? We know that when t is equal to 0, the initial position x is going to be equal to 1.5 meters. We also know the speed of the bottom of the ladder. So we know dx by dt. This is equal to 0.8 meters per second. And because the ladder is moving away from the right, that means that the ladder is moving to the right. I will interpret that as being positive. And then what I want to find out here is what is dh by dt, that we don't know, exactly 1 second later. As soon as it starts sliding down, within 1 second. As when I look at this diagram here, that's a right triangle, right? This angle right here is a 90-degree angle. That means that I can start relating my variables by using the Pythagorean theorem. This is the first thing that comes to my mind. I know, for example, that x squared plus h squared is equal to 25. Remember that x is changing with time and h is changing with time. So when I find the derivative of this equation, I have to be able to use implicit differentiation. That means that we're going to have 2x times dx by dt plus 2h times dh by dt is equal to 0. The derivative of 25 is 0. Now that I have that, our goal will be to find out what is the value of x precisely at 1 second, and also what is the value of h at 1 second. Notice that we already know dx by dt, so all that we have to do is to find x and to find h. Now I know that distance is equal to the speed times the time. So exactly when t is equal to 1, I'm going to have the speed equals to 0.8. Remember that the horizontal speed, the speed of the bottom of the ladder, is constant, times 1. That is going to give me 0.8 meters. This is really telling me that from time equal to 0, let me go over here. So imagine that at t is equal to 0, we know that distance is equal to 1.5. 1 second later, the distance is going to be 1.5 plus 0.8. In other words, I know that x will be equal to 1.5 plus the additional meters that we covered, 0.8. That is going to give me, very nicely, 2.3 meters. That's how I find x. So now I know that x is 2.3. Using the Pythagorean theorem, I can find h. H squared plus x squared is equal to 25. H squared plus 2.3 squared will equal 25. H will be approximately equal to 4.4 meters. Then what I will do now is I'm going to go back all the way to here. Since I already found the derivative, I already differentiated my equation, I am ready to substitute the values of x and h. In other words, I will have 2 times, I know that x here is going to be equal to 2.3 times dx by dt, this is the constant speed of the bottom of the ladder, plus 2 times h, we just found that this is equal to 4.44 times the unknown rate of change, dH by dt. That's going to be equal to 0. And then when we solve this equation, when we isolate dH by dt, we should get negative 0.41 meters per second. So when we're ready to state the conclusion, we will say, therefore, the top of the ladder, stating the conclusion in these problems is also very important, is sliding down. This is the key. By writing the word down, I will omit the negative sign. Is sliding down at a rate of 0.41 meters per second. In example 3, we have a water tank, which is in the shape of a cone. They're giving us the base, the radius, and the height, so we have all that information. What is important here is now the second part. Water is being pumped into the tank at a rate of 2 meters cubed per minute. So practically by looking at the units, they're giving me right away, they're giving me dV by dt, the rate of change of the volume with respect to time as the water is being pumped from the bottom of the cone. So I know that this is equal to 2, and I'm going to keep it positive because the water is being inserted, let's say, into the cone. Then they're asking us to find the rate at which the water level is rising. So as we are pumping water into the cone, we will see how the height is going to start changing. We want to know what is the rate of change of the height with respect to time. So that means that dH by dt is the rate that is unknown. Find the rate at which the water level is rising when the water, exactly when the water is 3 meters deep. So when h is equal to 3 meters. Remember again here, repeating myself, I shouldn't do any type of substitution until I have created my formulas and I have differentiated. After differentiation takes place, then you can go ahead and do substitutions if necessary. Well, in this case, it will be necessary. All right, so what is the relation going on here? Volume. So volume of a cone is equal to pi over 3 times r squared times the height. So here, it is important to realize that radius is changing with time and also height is changing with time. All right, so if I want to be able to use this equation and eventually differentiate the equation, I need to get rid of this r. I would love to somehow substitute r with something that is in terms of h so that I only end up having one variable, which is namely h. So in order to do that, when I look at this cone, I can think of similar triangles. I mean, look at this. This is the perfect setup for triangles that are similar. Using similarity of triangles, I know nicely that h divided by 4 is equal to r divided by 2. And if I cross multiply, I have that 4r is equal to 2h. In other words, r is going to be equal to h divided by 2. And now I can take this expression right here and substitute it into my r. So if I do that, we're going to have pi over 3 times h divided by 2 squared times h, and that's going to give us, once we simplify everything, that should give us pi over 4 times h. No, that will not be pi over 4. I apologize. That will be pi over 12 times h to the third. All right, So here is my relation. And this is the relation that I will now use to differentiate. So when I differentiate implicitly, because remember, age is changing with time as water is being pumped and that level of the water is changing, is increasing. So differentiating implicitly, dv by dt, that's going to give us pi over 12 times 3 times h squared times dh by dt. Simplifying, we're going to have that dv by dt will equal to pi over 4 times h squared times dh by dt. Now that everything has been differentiated, I can go ahead and take this h value and I can substitute it into here. I also know dv by dt, so the only unknown is going to be dh by dt, which is what I want. So continuing here, we're going to have 2 equals pi over 4 times 3 squared times dh by dt, and simplifying, that will give us that dh by dt is equal to 8 over 9 pi. What I want to determine now are the units of my rate of change. In the numerator, I have height, so then that's going to give us meters. In the denominator, I have time, so that's going to give us minutes. So the units of dH by dt are going to be meters per minute. This is practically the end of the problem, right? All that we needed to do is to find the rate of change of the height with respect to time. There's something very interesting that I want you to notice. I want to take you back to this step right here. I'm going to go ahead and substitute dv by dt. We know that this is not changing. This is 2 equals to pi over 4 times h squared times dh by dt. And I am going to isolate dh by dt. Actually, you know what? I need more space, so let me continue here. I am going to have 8 equals pi h squared dh by dt, which is going to be dh by dt equals to 8 divided by pi times h squared. So this is what I want you to notice, this expression. This is saying that the rate of change of the height with respect to time is inversely proportional to the height, the level of the water in the cone. Inversely proportional. So in other words, as h increases, as the height of the water in the cone increases, right here, because h is in the denominator, then this is really saying that the speed of the height is actually decreasing. And that makes perfect sense if you now think of what is really happening in the cone, right? I want you to imagine that we take slices of water, slices that are in the shape of cylinders. So I'm going to draw a very thin cylinder here, very small. I know that it makes no sense to think about slices of water, but pretend, and they're in the shape of cylinders. If you look at the cylinder that is below over here, this is a smaller cylinder. That means that the volume is smaller than the volume of the cylinder up here. So this is telling us that we need less water to fill up this cylinder in comparison to the one up here. So we're going to see the water level rising faster here than in the upper cylinder. And as the slices get larger and larger, imagine that I continue drawing another slice over here. Look at that cylinder. That cylinder is larger than the one in the middle. So the volume is going to be larger. That means that it's going to take longer to fill up, meaning that the water level is going to rise even slower. This is the effect of having this h right here in the denominator in the formula. In this particular question, let's see what is happening. A man walks along a straight path at a speed of 4 feet per second. So we can see the man over here, he's walking along a straight path horizontally. A searchlight is located on the ground 20 feet from the path. So right here, 20 feet, and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So imagine when here is the man, when he is 15 feet from the 90-degree angle right here, we want to be able to find the rate of change of theta with respect to time. So d theta by dt. All right, so I'm going to start writing things that I know is true, the given information. I know that dx by dt is equal to 4 feet per second. And this is exactly how the problem started. A man walks along a straight path at a speed of 4 feet per second. He wants me to find d theta by dt exactly when the horizontal distance is equal to 15 feet. That's what I want. Now, in this case, because I'm dealing with angles, right away I'm thinking of trigonometry, secant, cosines, tangents, and so forth. And I can try to find something that relates my theta and my x so that I can differentiate. In this case, I am thinking of beginning with tangent. I know that tangent of theta will nicely incorporate x in 20. Tangent of theta will be equal to the opposite length. So with respect to the searchlight, the opposite length is x and the adjacent happens to be 20. Then I can go ahead and I can isolate theta by considering tangent inverse of x divided by 20. And in order to find d theta by dt, all that I have to do is to differentiate this equation. So d theta by dt, I know is equal to 1 divided by 1 plus x over 20. I'm using my formulas for differentiating inverse trigonometric functions. And then times 1 over 20 times dx by dt. You have to remember that x, the horizontal distance, is changing with respect to time. So I'm differentiating implicitly. Now that I have that, all that I have to do once I've differentiated is to substitute the value of x. So when x is equal to 15 feet, that means that we're going to have 1 divided by 1 plus 15 over 20 squared times 1 over 20 times the rate of change of x with respect to time, which was given to me as 4. Continuing here, we are going to have that this is equal to 1 over 1 plus 3/4 squared times 1 over 5. And when I simplify all of this, I end up getting 16 divided by 125. Now the units, let's go back to our notation. We have d theta in the numerator. Theta is in radians. And then time, that's going to be in seconds. So then the units are going to be radians per second. Okay, so that's going to be the rate of change of theta. I'm hoping that you can handle the conclusion. Another way to do this problem, and I'm going to do it here on the left side in blue, is to, again, begin with the same relation, that tangent of theta is equal to x over 20. And then instead of using the formula for the derivative of an inverse trigonometric function, we're just going to go ahead and differentiate implicitly. So differentiating implicitly, the left side, we're going to have the derivative of tangent is secant squared of theta. But remember, theta is a function in terms of t, so times d theta by dt. And then on the right, x is also changing with time, so we're going to differentiate implicitly there as well. 1 over 20 times dx by dt. And then our goal is to isolate d theta by dt. That's what we want. So d theta by dt will be equal to 1 divided by 20 times secant squared of theta times dx by dt. And then that is going to give us 1 over secant squared is cosine squared. So cosine squared is going to come in the numerator divided by 20 times dx by dt. And notice now that it is possible to find the value of cosine squared. We have a right triangle right here. So by using the right triangle, I know that I can go ahead now. If you don't mind, let me continue here. Here is my right triangle. I know that this is 20. That doesn't change. This is theta. And then exactly when x is equal to 15, I can easily find the radius. The radius of this triangle using Pythagorean theorem will be 25. That means that cosine of theta is going to be equal to, again, with respect to theta, is going to be equal to the adjacent side. So 20 divided by the hypotenuse, 25, which reduces to 4/5. So by having that value, I can go back to my expression, the one that I had before, and I will have here that d theta by dt is going to be equal to cosine squared. So cosine squared in this case, let's say 4/5 squared, that's going to be divided by 20 times dx by dt, which is equal to 4. And that should give us exactly the same result, 16 divided by 125 radians per second. Okay, so two different ways of approaching the same problem. And usually that's going to be your decision as to which method you want to follow.